All right. Hi, everyone. My name is Marcelo. I work here at Suva, and I want to talk about one of our systems. It's called KEZ. I'll explain what KEZ means, but it's an automated system for coordination of document requests. Just a short overview. So just talk a little bit about Suva, what it is, about the machine learning platform, which is the team that I work on in Suva. Then give an overview of the business of KEZ, why it exists, and then get to the meat of it, which is the architecture themselves. Hopefully we'll get a very short demo working, and talk about the tools we use, and then also give some examples how we use Helm, because I think that's pretty cool, and then finish with some learnings and questions. All right. And also very important, the work here is not only for me, of course, it's a whole team. I even stole some slides from other team members, but they are fine with that. So just very quick about Suva. Does anyone doesn't know what Suva is? Okay, so just very, very quick. Maybe the numbers here are kind of interesting. So we have about 4,600 employees. Suva itself covers about half the whole accident insurance, or half all the employees, because it has a mandate to cover all the primary and secondary sector, plus 1/3 of the tertiary sector. So that's about 2.2 million people. It's close to the government, but not a government agency. I think that's a neat point. It's actually has a mandate to cover some types of accidents of professions, but it's not publicly funded. So it's fully self-funded, and it's also a not-for-profit, which is very nice, because anytime there is a surplus or a profit, it gives back to the marketplace in the form of reduced premiums. So in 2023, that was over 750 million Swiss francs. So that's pretty cool. And the machine learning platform that I work on here at Suva. So first, a little bit about the strategy, the constraints and goals for the machine learning. So the goal is to have a central platform for the operation of machine learning models at Suva. In our team, we define standards, how the models should be developed, and we also help them bring them to production. As goals, of course, the efficient use of resources, but also the whole packaging, monitoring of the whole applications. As a constraint, we have almost everything on premise. So Suva has this government mandate, so has strict requirements where the data should land. Plus, we deal with health data, which is another complicated. So we have almost everything on premise. We in the team itself have an open source strategy, so we try to use open source or free software whenever we can. But we, of course, are built inside Suva. So we use tools and infrastructure from Suva. For example, we use OpenShift, which is distribution from Kubernetes, and we use other tools which are not open. Yeah. And main strategy to deploy these machine learning models is package them in microservices and then integrate to different systems at Suva. That's also work we do. Maybe just real quick, the machine learning development cycle is very, very big. Goes from requirements to training, data exploration, and then optimizing models, getting them into production and monitoring them. And the monitoring is also not just the same as a normal monitoring, because we have to also have statistical monitoring of our system. So see if they are deviating too much from what is expected, and the whole thing back. So you can't do that alone. Usually we have not only in the team, but we have 3 roles that span all this. So from business analysts, which is very close to the business and knows what kind of data we have and what are good applications for machine learning. Then we have the data scientist, which takes that, explore this data, goes over, train the model, check if the model makes sense, until it comes to someone like me, which is a machine learning engineer, which will package that and bring that into production. And of course, because of the feedback, because of drift, that also goes all back. So the machine learning platform, we built or deploy tools that help data scientists to do their jobs. Here's just a splash screen with all the zoo, like a colleague of mine said, of things we have. Here we have stuff that we just deploy and use, like the whole log monitoring stack is Sentry, Prometheus, Grafana. But we also build some stuff. So up there we have the training runtime as an example. That's a way for data scientists to simply say, hey, I need that much CPUs, I need the GPU, I need that much memory, here's my code, go train my model for me. The data that they use for this model training is usually in the data repository, which is also a versioned way to keep track of all the training. And so these are self-built. So these things we built in-house, but for example, for the model registry itself, we just use MLflow. So just an idea. And also maybe what's interesting about that plot is that we have heterogeneous languages. So in the system itself, we have stuff written in Scala, and most code, or maybe all the code written by data scientists is in Python. So we have to bridge that gap. Cool, let's come to KEZ. So, a little bit of background, what is happening here. So some accident cases, they are more complicated than the rest. Maybe it's a case of multiple accidents, maybe it's a long recovery, but somehow these complicated cases need the case manager. Now the case manager tries to accompany the whole recovery process, and he needs access to all the documents related to that recovery. So sometimes an invoice comes and he says, okay, it's an invoice for an X-ray. So let's take a look, let's gather it. Sometimes physicians take a look on that, so we need the X-ray image itself. So he looks into our system to see if there is an X-ray for that invoice, and if they found it, yes, that's good. If they don't find it, they have to make a request to the hospital. All this cycle, it's done manually, or was done manually before. What KEZ tries to do is automate some of this. So KEZ means Koordinierte Einforderung von Zusatzinformationen, so something like coordinated request of extra information. And it's the system to actually try to automate this kind of request. Essentially, KEZ is an umbrella term. There's more subsystems. What I'm presenting is what we call KEZ a trigger, and the trigger means when an invoice comes for a few selected type of accidents. So these accident types or types of cases, these are the ones which are always complicated, they always need a case manager. So for these ones, in this situation, when an invoice comes, we automatically look for the documents because we know at some point they will need it. So our system looks into all our images we have or all documents we have and find out if it's there or not. And if it's not, already prepare requests. So say, hey, for this invoice, for this case, took place at that time, and for this hospital, please send a request. And that's still done manually. The release is done manually by the case manager. But if it works well and for a long while, we may even automate that. So let's get to the architecture thing. A very, very simple architecture goes from left to right. We start by one of our main jobs, which is integrating with other systems. So we would wish that our system would write directly to our Kafka topic. So that would be a Kafka topic here, but it can't right now, or it couldn't until now. So what we have, it's a crawler. So this one goes to a database where all the relevant cases are listed. And it's triggered from outside when the data is ready. This crawler simply gets that and fills a Kafka topic, and then we get to our collector. That's a Scala application that for each relevant case looks for which invoices could be relevant. So there is a time range, there is a type of invoice that does the collector. Once it has all the relevant invoices for a case, it writes in another Kafka topic where the matching service takes place. That one is a Python service and was written by data scientists. That one actually looks for images, looks for documents. The cool thing is that the documents, well, the data science, the model part is that the documents are classified according to types. So it's not just any report, it's a surgery report. And it looks for that. If it finds, it's all good. If it doesn't find, it prepares the request and writes in a Kafka topic. Now, that's a good thing. Before, we had another box here that would read from this Kafka topic and make SOAP calls to our downstream system. Now, the downstream system can read from Kafka, so that's already really pretty cool. And they work so that will be integrated with the business process management system. Down here, we have a small box that's actually a very, very small application, which we use just to persist the data from the topic into a DB. And when I'm talking about Kafka, I'll explain why. Just some things. So I said we connect everything with Kafka topics. The first part uses Tekton. I'll talk a little bit about that, how we use it. And all the other components are KEDA scaled. And behind the scenes, which was not there, it's all another few cloud native projects that we use. Keycloak, our Imaging Harbor, Prometheus for the monitoring, which I mentioned before, and also Helm, which will come to a small demo afterwards. On the right side, back on track. Here's just one of our it's an integration layer. We can see we have the event listener running. We have also a small application that exports metrics for us, but not relevant here. And now here I'm gonna make just a call to see how it starts. So I call the event listener, and then I can explain a little bit here. Here is our snapshot of our monitoring. Let me get the last 5 minutes so it's easier to see. So we can see here now that the crawler pod started. It will take maybe 1 or 2 minutes, and it's going to be filling up the first topic. And then once we have a few message there, then we start a collector. And first we start with just one, so KEDA will start to 1. But as you see quickly, we have here over 30,000 messages already. So it's already starting to make more copies. It will scale up to the maximum, which is 3. And, and once it's in 3, it's going to stop scaling, and at some point we'll get the first message to the second topic, and the matching service will start, which is that one, which already started. That's pretty cool. It actually worked. And down there, that means that some of them are already being processed here, so they're in the output topic that's already being copied to the DB. So, like I mentioned, I believe everyone knows Tekton, but just a few words. It's a cloud-native framework to build CI/CD systems. It's an operator with multiple custom resource definitions to build pipelines or deploy pipelines. And it's a project from Continuous Delivery Foundation. But that's not exactly what it is for us. For us, it's mainly a pipelining tool. So we don't use it as a build tool. We use it as a pipelining tool. And it's for us, it was very easy choice because it's already integrated with OpenShift. For general pipelining, there are other tools, but that one was just there, and it's good enough for us because we only need a trigger, like I showed, and we only need one single task, the crawler, which will start. So for that, it's a perfect use. Now a little bit about Kafka. So it's a distributed stream platform. Goals are high throughput, being persistent, and in a pub/sub model. And it's Apache Software Foundation. And what is Kafka for us? Well, Kafka for us, it's pretty much a distributed high throughput persistent pub/sub messaging system, with the caveat that we don't take the persistent too seriously, in the sense that whenever we need to persist some data related to a model, we are usually using that for analysis afterwards or for traceability. And for that, it's much easier to have them in a structured manner. So usually we take them out and put it in a DB. That's what the last box down there does. And we actually use Kafka to give us cheaply or easily a parallel workload. So all our topics per default comes with 16 partitions, which we don't plan to scale more than that, but we can easily, like we saw, easily scale up. And it also gives us the durability and self-healing aspect. So whatever DB is offline or whatever the reason, our components just fail, and it's fine because we have at least once a guarantee, so they will come up and work on it when the thing is back. or we'll get a poison message and we'll have to do, but then we have to do it anyway. And it's also become a standard for the streaming inside Suva. I mentioned you how we use it, it's the communication between all our systems. What's also very important for us that Kafka does is that it decouples the components. Like I said, some of our components are written in some different languages, and having an Avro schema in between is a good, clean API for that. For KEDA, that's pretty much straightforward. So it's a way to extend the autoscaler for Kubernetes. So the autoscaler for Kubernetes is relatively limited. KEDA allows to scale to 0. KEDA allows also to have some triggers which are pre-configured. So for us, it's mainly a point of resource management because, for example, in this cats trigger situation, we have a batch that takes maybe half an hour and that runs once a day. So it would be a complete waste of resources to have the things running. So for us, it's very, very important. And we use the Kafka legs to scale up and down. So that's pretty cool. Now going to this point about Helm, because Helm is a very interesting tool. It's a tool for managing Kubernetes resources. So we have many YAML files. You can simplify them in charts. It's also a tool for deployment, makes deployment of multiple YAML files together very easily, makes rollback easily, and it's also a templating tool. So you could use a chart and then just substitute some values and deploy your system. That's also Cloud Native Computer Foundation project, and we use it also as a deployment tool, but for us, it's also very important because we use it as an end-to-end testing tool. Like I showed, we have multiple components which are connected with Kafka. We have DBs around. Usually our systems are like that. So it's very hard for us to test everything just locally with just one component. So what we do, we use Helm to deploy in a namespace, mock DBs and mock servers, and have the whole system there. And we can then actually have end-to-end tests. And for us, the templating goes further. It's a full standardization tool for us. We use it not only so that we can change a few configurations, but we use it also to standardize the use of a lot of things. For example, Prometheus is just a flag in our chart. We can just subchart it, say, hey, Prometheus true, and then the annotations, everything is ready. And that's what I want to show, and I think I need to sit down for that one, because I think that's a very powerful way which we abuse Helm. So here's our main Helm chart, so the one that we pretty much use in all our components. It has normal stuff like image name and stuff like that. We allow to override, if we want, the commands and arguments, for example. We have some default values, for example, for replicas, which if you're just starting out, that is usually enough. Like I told here, with the Prometheus metrics, so the thing that sets the annotations for everything is just a simple flag for us. We use also to have some conventions. For example, we use port 8080 for everything. So that's also practical for us. And it's a pretty long thing, about 500 lines long. But what it allows us is to have a very simple one. So for example, something like that, where we just say, hey, look, I want this image and I want that, and I can just template it. And then when I get that, I already get not only my deployment, so I think the name is different in Kubernetes, I'm not sure, but it's an OpenShift deployment. We have things like the Prometheus annotations already, and for every deployment we have, for every pod, we have a service anyway, so there is a service for that with our default port, and a few things like some environment variables that we set everywhere. So that helps us to get that started. So whenever you're building something, it's very fast to get the first things going, and it's very fast to also add new things. So if here I'm gonna see, I've already pre-calculated. So here, for example, if I want a route or an ingress, it's called in Kubernetes, I can just say, hey, enable true, and get my host. And if I run that one, that one. I not only get the service and the deployment, but I get a route with already the service pre-configured. So that's pretty neat. Helps us also mitigate errors. Now let me show you how we do with KEDA, because KEDA is also very simple. We can just say, please enable it. It's going to be a Kafka trigger. I want this consumer group and this topic. And once I get that, what I get back is the whole thing as before, plus the scaled object down here, already configured with my Kafka. And as convention, we have a few secrets. So the credentials have all the same name for Kafka, so they can actually just get from here. So that's very practical for us. Maybe not very general, but for us, it's very, very practical. And the last thing I want to show, which is pretty cool, is that all our applications, we essentially build them without any authorization or authentication. What we do, we slap on top of them a reverse proxy, an OpenResty reverse proxy. And what helped us a lot is because we only had to get the Lua code right once, because it's pretty complicated. That one. So if you want to add OpenResty, we just say, for example, we have a route, we say it's true, we give a keycloak URL, client ID. For example, we say for all locations, I want authentication to be true, and I can give a list of rows, which will read in from the JSON Web Token. And the thing we get back is something like this, with the whole configuration of OpenResty in a config map, including our other default port. So whenever we have a protected port, we listen in the 3000. It configures our keycloak client down here, has some code to check for the roles already built in. Down here we have all the say endpoints that we want to be open anyway, like about and metrics. Plus, it configures the Prometheus on the reverse proxy, so we get metrics regarding calls and status errors, stuff like that. Also already deployed in a metrics endpoint. And our service then gets turned around so that whenever you call the 8080, actually you go to the 3000 target port, so the 8080 actually is not open anymore. And you can go directly to 3000 port. And in our deployment, we have, together with the main application here, we have down here an OpenResty application which is listening to that port, to those ports. Yeah, so it makes all the bindings for us. So that's it for that. Now we have to come to some learnings because not everything is roses. So for us, the use of language and framework agnostic tools like Helm, like OpenResty, like KEDA, it's very, very helpful because we can actually abstract away. We don't need to code in a lot of things if we can use this kind of tools. We abuse a few tools like Tekton, and for that we miss some features. For example, we would love to have an overview across all our namespaces, what are the pipelines, and maybe have advanced scheduling, which we don't. But for us, that's enough, and what we have is enough. And the trade-off would be if you wanted to, I don't know, have Airflow or something, that we will have to actually deploy it and take care of it and all that. A few points about Kafka. Debugging is much harder when we do this connection with Kafka topics. We actually need to have these end-to-end tests. We need to deploy them to actually get a good debugging. So that's a little bit slow and cumbersome, but I think it's worth it for us because end-to-end tests, we write it anyway. It's the type of test that goes to the business analyst and say, hey, look, that's what you're expecting in the end, right? So that they can read. So that's already something we'll do. And that's also privilege that we don't actually have to deal with the Kafka complexity because the cluster is a central cluster that we don't build, so we just use it. And also the connections for these consumers and producers, just ready-made libraries. We don't have to deal with much with it. So yeah, we're getting a little bit spoiled there. That's it, and thank you for listening. Questions? When there are none, then nothing stopping us from an apero.